To explain the fundamentals of osmosis and reverse osmosis, the following model will be used. It represents two reservoirs with a connecting tube separated by a piece of semi-permeable RO membrane. As stated, this RO membrane allows water molecules to pass through, but not hydrated ions or other larger waterborne species. We will show three examples using this model. In this first example, the tank on the left holds pure water represented as blue liquid. The tank on the right holds an equal level of water and sodium chloride solution represented as green liquid. Over a period of time, the level of water on the pure water side will drop, and the level of water on the other side will rise, appearing to defy gravity. This phenomenon is called osmosis. Osmosis occurs due to the attraction of water molecules on one side of the membrane to ions on the other side. Because hydrated ions cannot pass through the membrane, water molecules from the pure water on side A must migrate to further surround the hydrated ions on the other side. Actually, water molecules travel in both directions across the membrane due to molecular activity, which is influenced by temperature, but water molecules that travel from the pure side through the membrane spend more time on the dissolved solid side than do water molecules traveling the opposite direction. This occurs due to the attraction of the water molecules to the ions on the higher concentration side. As the water level on the impure side of the model rises and the level on the pure side decreases, the difference causes an opposing pressure that resists the migration of water molecules. Being that pressure exerted by water levels is known as hydrostatic head, this opposing pressure is known as hydrostatic head differential. It is a pressure which is basically caused by the level on one side being higher than the level on the other side. As the difference in fluid level increases, the ability of water molecules to continue migrating from the pure water side decreases due to an increased number of water molecules trying to migrate in the opposite direction. Therefore, one can see from this example that the process of osmosis will occur due to the attraction of water molecules to ions on the other side of the membrane. One can also see that the process will be limited by the difference in water column heights, which occurs as a net migration of water molecules travels from side A to side B. The actual attraction of water molecules to the hydrated ions has been measured to be about 1 psi per 100 ppm. Psi refers to pounds per square inch, and ppm refers to parts per million. On the other hand, pressure exerted by water levels, known as hydrostatic head, has been determined to be 1 psi for every 2.3 feet of water height. In this new example, the following concentrations and osmotic forces will exist initially due to osmotic pressures alone. At this point, the level of both solutions is equal at 11.5 feet. Therefore, since every 2.3 feet of water column height exerts a pressure of 1 psi, each side exerts a hydrostatic force of 5 psi, caused by its 11.5 feet of water column height. Solution A, located on the left side, has a concentration of 100 ppm of dissolved sodium chloride, which causes a 1 psi osmotic attraction in the direction shown. Solution B, located on the right side, has a concentration of 1000 ppm of dissolved sodium chloride. Solution B, therefore, exerts an attractive force of 10 psi in the direction shown due to the osmotic attraction of its dissolved solids. Because the osmotic pressure on side A is 1 psi and that of side B is 10 psi, the net osmotic pressure, which is the difference between these two values, will be 9 psi in the direction of side B. Taking into account the other forces acting upon the water columns, the total driving pressure towards side A equals 6 psi and towards side B equals 15 psi. The difference between these driving pressures determines the net driving pressure, which is also 9 psi upon initial conditions. As the water molecules migrate from the less concentrated side to the more concentrated side due to osmosis, the driving pressures change, due to the rising water, which creates hydrostatic head differential, and the changing levels of concentration. When the total driving pressures from each side equal the same amount, and the difference becomes zero, the net driving pressure reaches a state of equilibrium and osmosis will stop. When side A has dropped in column height from 11.5 feet to 5.75 feet, and side B has increased to 17.25 feet as shown, the following concentrations and osmotic forces would exist. Solution A will have a concentration of 200 ppm due to the fact that it has the same number of hydrated ions that it started with, but only half the total volume. Remember that only water molecules passed through the membrane, so all of the hydrated ions are still present. Side A will have an osmotic attraction of 2 psi and a hydrostatic head pushing in the opposite direction of 2.5 psi. Solution B will have a concentration of approximately 700 ppm due to the dilution which occurs when pure water migrates to side B from side A. Side B will therefore exert an osmotic attraction of 7 psi in the direction shown, and it will exert a hydrostatic force of 7.5 psi in the opposite direction due to the new water height of 17.25 feet. At this point, the net osmotic pressure is 5 psi, but the total driving pressure on each side has evened out at 9.5 psi. As a result, the net driving pressure has reached a state of equilibrium, and water level changes due to osmosis stop. In this example, side A and B have the same fluid levels, but the concentration of dissolved solids on side A is 200 ppm, while the concentration of side B is 5,000 ppm. Side A will have an osmotic attraction of 2 psi, and side B will have an attractive force of 50 psi. The net osmotic pressure of the system shown would be 48 psi towards side B. However, if we apply an additional pressure of 100 psi on side B and take into account the 5 psi of hydrostatic head, the applied pressures would equal 105 psi towards side A and 5 psi towards side B. The net driving pressure will become 52 psi towards side A. Basically, the added pressure causes more collisions between water molecules on the more concentrated side of the membrane, which forces free water molecules to be pushed across the membrane as shown. Remember that only water molecules can pass through the membrane, and they will pass in the direction that the net driving pressure pushes them. Reverse osmosis occurs when enough pressure is applied to cause a positive net driving pressure in the direction opposing osmosis. That is, a concentrated solution is squeezed by the application of additional pressure to force water molecules to migrate from a more concentrated solution to a less concentrated solution. This in turn means that seawater can be converted to purified water through the use of a semi-permeable reverse osmosis membrane and the application of adequate pump pressure. This is very important when one considers that over 75% of the population in the United States lives within 100 miles of an ocean. As this process is used to purify many water sources, including seawater and wastewater, there are limiting factors. One of the most significant limiting factors is the degree of concentration. Osmosis will stop when the concentration on side B of the model becomes high enough that its osmotic pressure cancels out the additional pump or piston pressure being applied. For the example shown, with an additional applied pressure of 1009 psi, this occurs when the volume of side B has decreased to 1/20th of its original volume, and its corresponding concentration has increased to 100,000 ppm. The increased osmotic attraction of side B combined with the increased hydrostatic head of side A has evened out the driving pressures. When this condition has occurred, the net driving pressure has become zero. This illustrates the need for reject flow. Any solution, no matter how diluted, will eventually concentrate enough to shut down a reverse osmosis system. Therefore, the following conditions must be maintained to allow reverse osmosis to occur at a reasonable rate. Fresh feed water must be provided and concentrated water discarded to prevent osmotic pressures that cannot be overcome by the feed pump. Membrane surfaces must be kept clean to prevent particle fouling from blocking water passage through the membrane. Concentrations cannot be increased to a point where hydrated ions get too close to one another, causing precipitation and scaling to occur.